Located in Hobart, capital city of Tasmania, is the new Tasman Bridge. The longest pre-stressed concrete bridge in Australia, a striking landmark amid beautiful surroundings, it ranks with such famous structures as the San Francisco Golden Gate Bridge and the Harbour and New Gladesville bridges in Sydney. Imposing and majestic, the 1-mile-long Tasman Bridge provides a new era of convenience for the Tasmanian motorist and a boost to the tourist trade. The first bridge to span the Derwent at Hobart was the unique floating arch bridge with a lift span commissioned in 1943. Its capacity was soon taxed by the growth of the eastern suburbs, and the raising of the lift span caused extreme congestion. In its lifetime, 51,000 vessels passed under its span, many of them at peak times, for the big ships could not be halted for motorists. Queues of cars, buses and trucks sometimes extended for 3 miles back. The need for an uninterrupted passage became increasingly urgent. The Tasmanian government approved a report by the consulting engineers Monsell and Partners for a high-level viaduct-type bridge which had the advantage of providing a clear passage at all times for both shipping and road traffic. The Minister for Lands and Works, the Honourable D.A. Cashin, MHA, signs the contract in the presence of the Director of Public Works and representatives of the contractors and the consulting engineers. Excavation for the main abutment on the eastern shore began in 1960. The dolerite rock on which it is founded is some 20 feet below water level. Altogether, 150,000 tons of concrete was mixed and moulded on this site. The beam units, anchor blocks, the bow tie crossheads and column vents, which were to form the building blocks of this unique bridge, were cast with exacting precision so that each could be fitted into its place over the water. The superstructure of the bridge is of pre-stressed concrete construction, mainly composed of large precast segments made in one or other of the 2 casting yards adjacent to the bridge. All reinforcement for these units was prefabricated into complete cages prior to being set in the molds to provide access for the pre-stressing cables. The 70-foot-long beams for the eastern viaduct were also of precast construction, the concrete being compacted by external vibrators bolted to the molds, supplemented by poker vibrators. Meanwhile, the concrete columns for the eastern viaduct, some almost 100 feet in height, were constructed in situ. The beam units were water-cured for 7 days, then stacked on both sides of the casting bed until required for jointing into finished beams. Fitted with wheels, they were moved to the assembly area on the eastern viaduct. The next operation was to erect the beams in position on top of rubber bearings by the use of a 45-ton mobile crane. With all 6 beams in position in one span, precast slabs were placed in position between them to form the lower half of the deck slab and to support the 3.5-inch thickness of in-situ concrete. The length of the bridge across the river is supported on 54-inch diameter Braithwaite piles, and the nature of the strata underlying the river bed is shown on the model. It will be seen that the major part of the bridge is founded on either basalt or dolerite at depths up to 160 feet below water level. Beneath piers 4 to 8, the dolerite is 300 feet below water surface and is overlaid by very stiff clays, a thin layer of coarse gravel, stiff sandy loam and a conglomerate. At piers 4 and 5, the piles are founded not in rock, but in very stiff clays, approximately 200 feet below water surface. The deepest pile is one located at pier number 7, in fact the deepest in Australia, a maximum depth of 265 feet. Normally 8 piles form the group beneath each main viaduct pier. There are 24 piles to each of the piers flanking the navigation channel and 12 under the 2 adjacent piers. The majority of piles have a 1 in 12 rake from the vertical, thus giving the piers a very much greater resistance to horizontal forces. A floating template positioned and held the piles at the correct rake and braced the group together until the first lift of the pile cap was completed. Each pile was formed within a 54-inch diameter tube made of 3/8-inch mild steel plate. The 30 feet long sections of tube were welded together as the tube was sunk into the river bed. The cutting edge at the bottom of the tube was of thicker plate to avoid damage and collapsing of the tube. This tube was initially sunk to founding level by the combination of grabbing spoil from within the tube and twisting the tube itself by means of hydraulically operated oscillators which grip the outside of the casing. The deck of the pontoon formed the template for the first layer of the reinforced concrete pile cap, which was constructed above all but the highest tides to minimize the need for working in water. A reinforced cage and 2 grout pipes were placed inside the pile for its full length. Stone was then placed in the tube and the voids then injected with colloidal grout. The grout tubes were withdrawn as the grout level rose within the pile. The concrete for the pile caps was mixed on a special barge and pumped to its final position. Once the first pour of concrete had strengthened, the template was lowered and withdrawn. This cross-section shows that the bridge contains 4 11-foot traffic lanes throughout its length and 2 4-foot 6-inch footpaths, the overall width of the bridge being 57 feet. The bridge deck generally is formed by 6 longitudinal beams, together with a part precast and part in situ deck slab. 3 steel stagings, each weighing about 500 tons, were provided to form a working platform for the crane and to support the columns whilst they were being assembled. With the aid of these stagings and the 100-ton Goliath crane, the first part of the main viaduct was completed in a similar manner to that of the Eastern Viaduct. All the columns were designed to be flexible, with the exception of the 4 pairs of columns in the navigation and anchor spans. After being floated out, one of these column units for the navigation span is seen being lifted into position. The precasting technique was adopted primarily to permit rapid erection over water. Each of the 4 column pents beneath the navigation span consisted of 8 hollow sections, the largest of which were 12 feet by 10 feet in cross-section. The crossheads of these columns also consisted of hollow precast boxes stressed together with macalloy bars. With the crossheads in position, fine concrete joints were formed between the segments and the units pre-stressed using macalloy bars. The high tensile bars having been stressed, the pre-stressing jack was removed and each duct sealed with liquid cement grout to prevent corrosion of the bars. The main navigation span is 310 feet, with a minimum shipping clearance of 150 feet above mean sea level. The navigation span beam units up to 16 feet deep and 40 feet long were cast in sections and floated into position. The individual beam units weighing 50 tons were supported on the top of temporary staging and jointed and stressed in situ. The joints were formed with fine concrete cast in 3-inch gaps left between the units. The beams were then pre-stressed in 3 stages using 1-inch diameter strand. A number of strands were first threaded through from one end of the beam to the other, past numerous separator blocks using a pilot cable. This high-tensile strand, which was imported from the UK, arrived on site in 3,000-foot coils, the required length of each strand being cut by electric saw. A stressing jack was then inserted, one at either end, for the stressing of each cable to 48.5 tons, and the wedges rammed home. Having completed both sides of the navigation span, 110-foot-long central drop-in beams were erected, and the main viaduct erection then continued toward the west. Work also proceeded in the fabrication of the main viaduct precast units, columns, bow tie units and crossheads, these larger 100-ton units being fabricated in Montague Bay. At the same time, the steel stagings were continually floated around and positioned in readiness to enable the Goliath crane to erect the next column bent and set of beams. The main viaduct column units were towed out from the precasting yard to within the reach of the crane. To position the McAloy holding down bolts, the first 2 column A units were located on rubber pads. After being plumbed and aligned, the units were grouted at the base and stressed to the pile cap. When all units were in position, the joints between them were rammed with dry mortar and the whole stressed together with McAloy bars. The column A units fit snugly into a preformed recess in the pile caps. Portable radio sets were used to advantage in the erection of these large units. The McAloy bolts were threaded and tightened by lever prior to stressing. A check on the depth of the thread, then the McAloy pre-stressing jack took over and the units were securely anchored to the pile cap. Finally, mortar was pumped into and around the recess to prevent corrosion of the bars. As explained earlier, Montague Bay was the center of activity for the fabrication of all larger precast units, which could not have been conveniently handled any other way than by water. The flexible main viaduct column bents generally consisted of 6 precast sections, the maximum size being governed by the 100-ton capacity of the Goliath crane and the height of the particular column. Each column bent is 2 feet 6 inches thick by 10 feet wide, and the tallest is 125 feet high. These columns were stressed at the pile cap to give a rigid connection at this point, but free to rotate relative to the deck beams, and were designed as propped cantilevers. Lateral forces on the superstructure were resisted by the portal action of these bents. The crossheads are of heavily reinforced concrete construction. Notice that by now most of the western main viaduct had been erected, and the gap for the old shipping channel had shortened considerably. The main viaduct column bent, having been fully stressed, the McAloy bars were then protected by liquid grout, which was pumped around the ducts, working from the base of the column to the top. A foreman observes grout spilling over, which was a sure sign that the duct was filled. The ends of the grout tubes were then bent over and sealed with concrete. Meanwhile, main viaduct beams were stored on deck and, when required, were brought along the finished concrete deck from the assembly area to the Goliath crane and lifted forward into the next span. Special beam transporters were used, the beams being winched up and over the deck under the direction of an engineer. The cycle of operations for beam erection was as follows. The crane picked up an all-aluminium lifting truss and positioned it on top of one of the main viaduct beams. The beam was then lifted from the deck, ready for erection on top of the crosshead. Remember, each beam weighs almost 90 tons. The beam was then carefully lowered into position on stainless steel sole plates and the lifting truss removed for the next beam. After the first two beams had been erected, the columns were jacked over a predetermined amount to allow for subsequent shortening of the deck due to shrinkage and creep. The remaining four beams were then brought along the deck and erected in position. With all six beams in position, the precast deck slabs were laid between adjacent beams, additional reinforcement fixed in position, and the in situ concrete poured to complete the deck. After the deck had been poured, timber shutters were fitted for concrete diaphragms connecting the six beams over each crosshead. The two main piers on either side of the main navigation span are protected by massive gravity fenders. The impact of a ship striking these fenders causes them to swing and be lifted on their supports. These gravity fenders have been designed to absorb a glancing blow from a 20,000-ton ship traveling at 9 knots. The complete fender to each pier weighs 1,700 tons. The two gravity fender rings were fabricated in sections and jointed in Montague Bay, then floated out into position and the two half sections reunited. These 8 box-like units with 9 feet deep walls, 5.5 inches thick, were cast in 3 lifts in timber molds. The fenders were then raised with lift slab equipment and all 8 box-like sections then filled with concrete. The permanent anchorages were then concreted at the 4 corners, and then flexible suspension links fitted into position around large top and bottom anchorage pins. Finally, the fender unit was completely supported on all suspension links and the temporary lift slab equipment removed. With the Tasman Bridge almost completed, the floating arch bridge, weighing almost 25,000 tons, had then to be removed. The plan was to part the arch at its centre and swing back the eastern half, leaving the western half secured to anchors at its midstream end. The eastern half was then towed away upstream to Geilston Bay. The western half was to be disconnected at the western abutment and rotated about its midstream anchors and eventually towed away. In order to restore river traffic, which had been stopped for 3 weeks, some urgency was needed to complete the first part of the operation, but there was also urgency to move the western arch to safe anchorage because of the danger that it could break loose in stormy conditions and perhaps be carried down onto the new bridge. To make sure the operation could be carried through almost regardless of the weather, 2 large, powerful ocean-going tugs were hired from the mainland as prime movers. When the centre pin had been removed, the eastern section was swung back with the aid of these tugs. The eastern shore link was then severed to the delight of many Hobart sightseers. The tugs then towed the eastern half arch to Geilston Bay. The western half arch, which up to now had been held fast by concrete anchors on the riverbed, was disconnected from the western abutment and rotated upstream, then towed to Geilston Bay. Immediately prior to the removal of the old bridge, the new Tasman Bridge was opened to traffic by the use of a temporary bypass bridge. The temporary structure in the vicinity of Pier 2, or the old navigation channel, consisted of 2 of the steel stagings supporting a 2-lane temporary roadway. Between Piers 1 and 3, therefore, the permanent concrete deck was constructed in 2 halves. The beams for the closure spans were then erected. As before, the beams were seated on stainless steel sole plates and deck slabs fitted. Concreting of this half section of deck allowed traffic to use it and the temporary roadway to be removed. The remaining half section was then constructed. During the period of construction of the Tasman Bridge, both the western and eastern approaches were also being built. Certain finishing work, such as concrete parapets and curbs, were carried out and followed closely behind the main structure. Steel handrails and safety rails were also fitted to both sides of the bridge. The Hydroelectric Commission installed mercury arc lamps used to light the roadway. The decorative strip lighting and flood lighting along the entire length of the bridge was carried out by Claude Neon Limited. Throughout the project, over 450 workmen were employed. Construction workers, engineers, divers, foremen, all skilled in their particular field. The use of 2-way radios played an important part in the smooth running of the whole operation. After a construction period lasting over 4.5 years, the bridge was completed and traffic flowed freely. On the 29th of March 1965, His Royal Highness, the Duke of Gloucester, officially opened the bridge. At this ceremony, there were many visitors from the United Kingdom and the other states. Tasmanian manpower and resources were used to a major degree, and the bridge has made an important contribution to the economic health of the state. The chosen design enabled a far higher proportion of materials such as cement, steel and timber to be obtained or fabricated within Tasmania. It is estimated that at least 8 of the $13 million spent on the bridge found its way back into Tasmanian pockets. Tasmanians have a bridge, a magnificent engineering achievement of which they can be proud, a worthy addition to an already fine harbour.